to computer vision and object detection with Detectron II. So before I start, I'll just introduce myself. Hi, I'm Christy. I look a little bit different from the picture now with my weird quarantine hair experiments, but I'm in 3B computer science at the University of Waterloo. I have previously interned at PayPal and Google as a software engineer. Haircut's fresh, not gonna lie. Thank you. You're too kind. And I'm currently interning at Cockroach Labs. My Twitter handle is gaoxiuxiuk, and there's more contact information on the hack pack as well. So what are we going to talk about today? We'll go over the goals that we're trying to accomplish with this workshop, what computer vision is, some computer vision problems. We're going to look at some traditional solutions and some deep learning solutions. We're going to go through a really quick Detectron II coding example and talk a little bit about how to put it all together for a hackathon project. And there's some further reading at the end as well. All right, for today's goals. So today we're obviously going to talk about computer vision. We're going to talk about some concepts, some problems in the area, high-level solutions. We're not going to get into the nitty-gritty. And we're also going to be using an existing model for object detection. Today, however, we will not be training our own models. I also don't suggest you do that for a hackathon either. It's going to take a ton of time. And we're also not going to be doing an in-depth guide on machine learning tools. There's a different workshop for that I strongly encourage you to check out. All right, so let's jump right into it. What is computer vision? So a good question to ask ourselves first is, what is vision? When we think about our fleshy human bodies, we know there is the real world, and we have a sensing device, say our eyes, where we get data from the real world that goes through the sensing device into a interpreting device. And the interpreting device will run something over it and come out with some amount of meaning. Now, what that kind of looks like parallel for computers is a sensing device might be a webcam. The interpreting device might be some code that's somewhere on your computer, and then out comes out the meaning. So in this case, that thing on the left-hand side, when I look at it, I interpret that it's a meme. It's kind of thick. It exercises clearly. It's a dog. It's a Shiba. And similarly, you can make take a sensing device that is hardware and take an interpreting device and output the same meaning. Absolute unit. It's just built different. So to kind of reiterate, what does a computer see? Images are actually just stored as height by width matrices, where each matrix entry represents a pixel. Now, the little grid on the side is just a number between 0 to 255. That's actually a little oversimplified for red, green, blue pictures, or RGB pictures. It'll actually be width by height by 3. The third dimension adds a channel for what amount of red, blue we're adding in. But that's a bit of an implementation detail. There's also CMYK. But yeah, images are just matrices of numbers stored. But again, what do we see? There's a lot of stuff to unpack here, right? It's a pretty topical meme, if I'm not a boomer. It's a sad white fluffy cat. There's a laptop in the midground. The laptop is on a website. We could maybe make a guess for what the website is. The room has white lighting. The room has shutters. The walls are white. Asgar said it's a pic after they did their stats final. There's a lot of information to interpret here, right? And also the eyes are photoshopped, but that might not even be obvious to most people on first glance. So there's really almost an infinite number of problems that we can attempt to solve just with one picture. So let's talk a bit about those problems. So like I mentioned, there's almost an infinite number of problems that you might want to solve just from one situation, but we can dissect a few common situations that we have some solutions to. So let's run through them real quick. So first is filtering. If you've ever posted anything on Instagram and, you know, you're about to post and you spend like 2 hours figuring out exactly which selfie you want to use, and then you see there's like, oh, there's 20 different filter options. Which one am I actually gonna pick? So filters are just shifting colors and applying math over that, you know, initial matrix that we talked about. And if you are at all familiar with digital art, the different blending modes in digital art are just applying a set of math on top of layers that you have underneath it. And so it's filtering in a very similar way. Transformations are another common problem in computer vision. For example, doing panoramas. When you do a panorama on your phone, you're really, you're taking the picture that's on the left and the picture that's on the right. They're going to be the same size, same position. But you need to, figure out how to transform the two pictures so that they blend seamlessly together and become a panorama. And similarly, you can get more complex than this. You can have those 3D panoramas where you can put your VR goggles on and take a look around, or that are posted on Facebook that you can click and drag around. And really, transformations kind of apply to a lot of the different editing tools in photo editing that are very basic, like tilting your pictures, straightening them, cropping them. That is all just a lot of algebra applied to these matrices that we've talked about. Structure for motion. This is a pretty cool area. You can take a video, walking around a tall building, or take a few pictures around a building, and you can actually generate a 3D model on an XYZ plane from those pictures. So that's another interesting problem to solve. And we'll get into the solution a little later. There's also depth perception. When you're just looking at a flat picture, which is 2D, how do you understand that third dimension that's missing there from just the flat picture? Even for like normal people, looking from this picture, the camera stand back here has a really similar color to the shadow stand. So that's also another really important problem to solve. How do we get seen? And then there's also segmentation. Segmentation is a bit of a loose term. It just describes segmenting, grouping things together. There's all sorts of segmentation problems you can solve. On the left, we have separating the foreground from the background. On the right, things are grouped together based on average color. And you can see this algorithm didn't quite get it in the middle, where it's mistakenly colored some blobs green. But you can see that with grouping together average color, you can start to get a sense of the structure of the rows that's imaged there. And of course, infinite problems. You can get more and more specific. You can look at once you've done that segmentation, say, okay, is this a person? Is this a horse? There's semantic segmentation where you can just say, this is all people. There's instant segmentation where you say, like, this is a person, and then this is a person, and then this is a person. It's a little hard to see on the right here. But this picture is an example of object detection. It actually comes from Detectron II, and it's segmented each of these horses correctly. It's also impressively been able to segment this horse as being a singular horse, despite having a person on it, and despite having to break up the highlighting. More people back there, another person, yeah. So that's just a bit about some of the problems we have, and I'll be getting into some of the solutions in a second. But before I move on, does anyone have any questions? All right. What am I drinking? I'm drinking green tea. It's in a Toronto Zoo panda mug when they were visiting. But back to the computer vision problems. Is computer vision just getting info from images? Yeah, a lot of problems are definitely about getting info from images. There's also, I had mentioned like the sensing devices earlier. Web cameras and like traditional cameras aren't the only ways that we're sensing information. LiDAR, for example, is used heavily in I'm at a loss for it, self-driving cars. And so LiDAR displayed as, you can display it as an image, but it really doesn't care about like, RGB values. It doesn't try to pick up on visual cues for shading or anything like that. It's really a different kind of paradigm of information that is stored. So it's not always just about images. I think our idea of images, the most intuitive way to understand it are pictures, as I've shown, but there's LiDAR. Medical imaging is also a huge field for computer vision that I'm unfortunately not as well versed in, but the way medical imaging is stored is also very different. If you've ever seen an X-ray, you know, it often doesn't have tons of color going on either. And the information is captured in a different way. X-rays captured with, oh no. My grade 10 physics is failing me. Some amount of UV exposure, I want to say. All right, how do you go about working with bounding boxes? How do you go about working with bounding boxes? I'll actually get back to this in a second. I think it'll be a good segue into another point I'll have about some of the deep learning solutions. All right. What level of math is necessary to work with the images in this way, and what are some problems we can approach with less math knowledge right off the bat? I would say if you want to like become a computer vision like expert and work in the computer vision area, you do have to study the math. Luckily, a lot of it is just linear algebra, so it's not like a trivial amount of studying to do, but it's definitely doable with the correct amount of hard work. If you want to be, if you just want to tinker with machine learning, computer vision, as long as someone out there has created a model and trained it and put it out, you can take it yourself and apply it however you like. But in terms of like doing research in this field, the math is quite important, even in the deep learning. It's okay, I failed very tense physics, me too. Yeah, how good do you need to be at math to understand CV at a moderate level? I don't think it's necessarily like how good you have to be at math. You just have to be willing to study some of the linear algebra that's required. And even if you like suck at it, honestly, like I suck at it too. The most linear algebra heavy parts of computer vision I really struggle with. But you can still understand it at a high level and be able to do some interesting, studying in that area. How to increase accuracy, just train with more images. Yeah, I'll get back to that in a second, though. It's really important what kinds of images you train with as well. In these types of problems, which do you think are the most underdeveloped and or new? Oh, sorry, I got distracted. Which ones are the most underdeveloped? I think, don't quote me on this, but I do feel like medical imaging is like super underhyped because the self-driving cars and the image analysis is like very exciting and very intuitive to understand, and like the medical imaging field as well just doesn't have as much like venture capital money funneled into it, right? So I think I've heard a lot less about the medical imaging field, but like I personally believe it's probably an incredibly important field. All right, I think some of these questions will be answered along the way. So if you all don't mind, I will move on to the next one. Anything easy tools to hack with computer vision for hackathon? Yeah, we will definitely be covering that today. How to get a computer vision related project up and going in time for hackathon. Yeah, we'll definitely be covering that. All right, let's get into the traditional solutions. So the traditional solutions, some people will also call it handcrafted solutions. This is really the aforementioned math I had mentioned, but just saying like, just throw some math at it, it'll work. It's a little less, it takes a little bit more intuition to develop, but I think the easiest way to think about it is if you've taken grade 10 physics and there was that optics unit, there's a lot of talk about light rays, and when they pass through a certain shape of glass, they will bend in a very deterministic way, and they will converge at a certain place. So all those details I'm not going to get into because I'm not a physics teacher, but when you take advantage of those features, it can really unlock a lot of solutions that don't require deep learning, just require a lot of linear algebra and thinking about it. So the 3D model from, the structure for motion that I had mentioned earlier, excuse me, a lot of that is being able to first match points, which we will get into a second. But once you've matched points, you can figure out how far away each picture was taken from each other, and then with that information, be able to reconstruct the structure in a 3D space. And again, this is just really taking advantage of the reliable geometry we have in the real world. We know that light rays will move a certain way. We know that a picture a certain distance from a point in the real world can be mapped into a different pixel on a different picture taken of the same view. So that's all just using that reliable geometry. And similarly, the depth perception I had mentioned earlier, how I mentioned, the camera stand, the coloring, the lighting cues, it kind of looks really, really at the same level as maybe that bookshelf or maybe the poster in the back or something. Especially when you don't have as much light shining on it, it's hard to tell just from shadows. And yet, most of the times we can still figure out that, oh yeah, the camera stands closer. And the interesting thing is that it's thanks to us having two eyes. When you have two parallel views of the exact same view, sorry, that was a little confusing. Two parallel views of the same setup, for example. You can try to give it a test right now. Like just pick a spot on the wall, close one eye, open the other, and you'll notice the objects closer to you move more across your plane of view, versus objects farther away from you move a lot less. So that is also reliable real-world geometry. We know that our two eyes, close one eye, open the other eye, objects closer to you will move more, objects farther away will move less. And so again, if you can match the features, and all you have to do is just figure out the distance that it's moved between your two pictures, and you've got yourself a depth map. How many of you just winked at the wall? Yeah. All right, so that is on depth map and structure for motion. But I mentioned feature matching. I've mentioned feature matching here. That's a bit of a tongue twister. So let's talk about that really quickly. Your wall feels appreciated. Yes, give your walls some love. As you can see here, I've thrown on some very questionable anime posters from when I was in high school. So love your walls, I guess. Yeah, so talking about the feature matching, over a very particular window, you can give an estimate within some degree that there is a straight edge in this picture, or there is a corner in this picture. Now, it might be a little complicated with the real world and colors and whatnot, so I want you to think kind of in black and white for a second. If you have a little window and one half is completely white and one half is completely black, you can kind of represent, if you represent that as pixels, you have one half that's completely zeros and one half that's completely 255 pixel values. And so it's, you can represent that strong difference in that particular direction with math. And this kind of feature detection can be pretty handy. So for example, if you ever had one of those crappy digital cameras in the 90s that were this big, and you held the button down for just a few seconds, if you're taking a picture of your family, usually a square would draw around the person's face. And it might be whoa, we didn't have deep learning back then. How do we do facial detection? A face is just two eyes and a mouth, and so if you work out the math for how to detect the shape of the eye, the two eyes and the mouth, then all you have to do is scan scan the entire image over your particular window and detect those faces and then draw your bounding boxes. So that's a bit on feature matching. And then on segmentation, so for foreground and background segmentation, it's really like, oh boy, here we go with this explanation. If you can feed a bit of data saying like, I know that this window here and this window here, these two blobs are the same, then you can try to connect them and select everything over your image that are very similar within some degree of error. So with the picture of the Shiba, you can see there's like 2 red dots on the Shiba and then a blue dot behind the Shiba. That was information put into that's information collected from the user. And the red dots represent that, hey, this is the foreground. The blue dot represents that it's the background. And basically the red dots like sample the Shiba fur and is like, okay, this is what the foreground looks like, and then tries to connect, pick everything within that's like a neighbor of it, if you think of this as a graph, that has a similar texture or color or whatever it is, until it's selected the entire foreground object. And a nice application of this is zoom backgrounds. And you might wonder, oh, well, I don't click on my face every time I move using a zoom background. I believe my guess is that zoom backgrounds use a combination of facial detection, which there usually are not a lot of if you're just in a meeting or a conference call, and using that as input to say this is the foreground, and pulling it all together. So that's just a bit on traditional solutions, and now we're gonna talk a bit about deep learning solutions. But I've been seeing quite a bit of action in the chat. Did anyone have many questions on the traditional solutions? Why not hook up a LiDAR sensor and a camera for better depth perception? I think you won't always, unfortunately, you won't always have your data served to you in the best format. So for example, if you say there's a YouTube video that you want to get the depth perception of, and you want to use the depth map as training data, chances are that YouTube video was not hooked up to a LiDAR sensor and a camera and uploaded at the same time. So there's definitely still cases. It's a little lazy to just say I mean, it's a little lazy on my part to just say oh, well, sometimes the right devices aren't hooked up, but from a pragmatic standpoint, that's just the reality of a lot of data collecting. Somalia. Why is the Shiba nose not marked as separate? Oh yeah. So that's actually a really good question, because the Shiba nose and eyes and collar look like a totally different thing. So like I mentioned, it's within a degree of error. And so what the algorithm in this situation would have seen is that everything around the eyes are collected into the same category and are seen as the foreground. And so if everything around it has already been confirmed as we're going to go with this for the foreground, then it might determine that the eyes and the nose are within an acceptable degree of error to keep it together as the foreground. That being said, well, maybe you could have made a cardboard cutout and punched out holes, and maybe it wouldn't have done such a good job, and that's why it's not a perfect solution by any means. You can see around the edges, it's a little rough with the grass as the background, kind of confusing it a bit. So it's definitely not perfect by any means, but that's a good question. And yeah, the concern about getting into ML as a high school kid, there's a lot of great 3rd and 4th year courses on this kind of stuff, and I really think by obviously I'm biased, but I think by taking a slow, disciplined approach to truly understanding programming fundamentals and computer fundamentals as well as math is really beneficial. And so I wouldn't worry too much about being in a rush. That by all means, though, if you're interested in this area, there's plenty of online courses and resources as people are describing in this chat, and also that I'll mention at the end as well. All right. Okay, I'll jump into the deep learning solutions then. But it looks like we have a lot of machine learning buffs in the chat. Unfortunately, though, I'm going to completely oversimplify the models, like understanding of models and deep learning. I'm going to oversimplify a lot of this because I think what's really important, especially for younger students, I don't think you have to learn all the math thoroughly, and I don't think you have to learn about convolutional layers right now or mathematical layers right now. What I'm assuming much of you are looking for is for a way to like get object detection or something along the lines of that, working on your hackathon project so that you can build a cool project on this weekend and present it and feel proud about it. And so we're going to talk about like the concept of models and generally understand deep learning, but I don't think we have to get too specific into convolutional layers, max pool layers, anything like that. They are very cool, yes, and conv and max layers are still very confusing to me in many ways, but yeah, so let's go hit this grossly oversimplified explanation of models. So the way I like to think about it is, especially like before I had started to really take a course that was deep diving into computer vision, is your model is a black box. And in your black box, you have some number of weights. Let's say you have like n number of weights. Now, you want to train this model such that it's, given an input that you're giving it, it's going to come out with a target solution. And how it's going to like smartly pivot itself towards getting to the target solution is you're going to give it a loss function that tells you, hey, I gave you an input, you gave me an output. This is the actual correct solution. Here's how you calculate how close you are to that correct solution. And once you have given all of this to your model, you can train your model over an incredibly large amount of data that is likely in a category that you're actually trying to make a model for. And after you've trained it on all this data, you've trained it on a lot of data, you've used your loss function to like pivot it towards the right place. After that point, you're going to have your weights in your black box tuned in such a way that once you start feeding it new data, so data that wasn't in your training output, it's going to start outputting information that you're looking for. So for example, your input and target solution, going back to that picture with a vaporwave looking Roman head statue thing, your input data might be that picture, and your output might be the complete, your ground truth disparity map. Someone has sat down and really picked out every pixel and said, this is how far away this object is from the camera. And I also want to mention that models, like deep learning, it sounds like an incredibly very cool new hot topic, and it certainly is. But the concept of models themselves haven't been, they're not hyper new. We have handwritten digit detection models as early as 1989. So the concept of models themselves are not super duper new. So why is it that now we're seeing a massive boom in machine learning, deep learning? Like, man, every high schooler wants to learn what machine learning is. I want to learn what machine learning is. My mom wants to learn what machine learning is. And it's so exciting because improved hardware technology has really opened up new opportunities for training different kinds of models. The digit detection, like going back to 1989, maybe this is just me, but when I learned that that was available in 1989, I was like, what? Like, no way! Like, what did people even have in 1989? Did they even have the internet in 1989? But it really is an increased access to hardware that has been incredibly improved, that lets us train data for hours and hours and come out with just a handful of hours, maybe even, and come out with a model that adequately does its job. The training that I mentioned earlier, like, honestly, man, like, you're kind of like brute forcing yourself to get those weights in your black box tuned. And so that takes a lot of time. It takes a lot of computer resources. And so the improvements we're seeing in hardware has really cut that time down and made it more accessible to be able to make these models. The ML hype train is too strong. Yeah. But yeah, so that's just a bit of me ranting. Let's talk about this slide here. So I mentioned the improved model, the improved technology that enables training. So I want to talk a little bit about loss functions. You can design really clever loss functions to improve solutions to existing problems. So on the left here, that GIF looks a little strange, but what it's actually doing is it's producing depth estimation for a video of someone driving around a street. And that video was actually taken off of YouTube. But when people post videos on YouTube, normally they don't hold two cameras and drive around at the same time and post both videos, right? Normally you only have one camera that's on your smartphone. So how are you supposed to do depth estimation if you only have one view of your environment? Well, with clever loss functions and clever solutions for training, you can create a model that maybe it's trained on both views. Maybe your input data does require a left view and a right view. But what you can walk away with is a model that can produce depth estimation on only a single view. So I think someone mentioned earlier that why don't you just add a LiDAR and a camera, and then get depth perception off of that. I think trying to use YouTube videos, for example, people usually just post whatever they could have taken with their smartphone, and that's usually only one view. But once you are able to make this model, now you can get really just scrape as many videos as you want off of YouTube and convert them into depth maps and do whatever you want to do with them. So that's an example of how you can really cleverly use your loss functions and maybe cleverly design your layers in order to get in order to improve existing problems. For example, getting depth estimation out of just one view. Another example is single view photogrammetry. I don't believe this area is as sophisticated yet, but I mentioned structure from motion earlier. There's also work being done in structure from no motion. So creating a 3D structure just from one picture. There's also classification and regression problems. This is some pretty spicy stuff that kids these days love. So kind of going back to that picture earlier of the dude on horse at that weird festival thing, you see these kind of blobs and also these bounding boxes, and they look kind of particular. They look a little weird, but what the model is trying to do is trying to give it's trying to take every single pixel and say, I have with 30% confidence that this pixel belongs to a horse, or I have 90% confidence that this pixel belongs to a horse. And then instant segmentation becomes oh, I have 90% confidence that it belongs to this horse and not that horse. So that's classification and regression. You're gonna have to, if you're the person designing the model, you're gonna have to really think about okay, I'm including what labels here? Horse, people, maybe I just want to use a cat and dog, maybe I just want to do cat and dog labelings. What are my loss functions there? The loss function for a dog and a cat are probably going to be different, right? So that's a bit about object classification. The left view is the most intuitive way to understand it. And then the right view is object classification in 3D LiDAR. That's also, again, in the self-driving car area, a very exciting research. And also a little less intuitive to understand, but very cool stuff regardless. All right, so now we kind of come back to that idea I mentioned earlier of we can really extract infinite problems from a single picture, and we can get into some really interesting situations to solve using deep learning, as well as generate some situations of our own, but I'll get to that in a second. On the left here, has anyone seen the movie Klaus? It's a 2D animation movie. It's a Christmas movie. It's very cute. Yep, awesome. Yeah, so there's this great YouTube video about how Klaus is made, and basically the animators animated the entire movie on the left side, where it's that flat image. I mean, his nose is a different color, but there's no shading on the image. And the really cool thing about what they did is they used a model to predict lighting onto their 2D flats. And what does that mean? That means the picture on the right, with that really great lighting, it almost makes it look like a 3D image. That was generated with a machine learning model. And this is just insane, I think, for the art community. Like, you can imagine a bit of a crisis of faith almost. The technical merit of some aspects of art are almost cheapened in a way. If you have a model to do all your shading, then you can hire quite a few less animators. Similarly, I didn't include a GIF here. I really should have, but there are lots of projects where they take animations that are in like 30 frames per second, and they run a model over it, and it converts it to 60 frames per second. Like, you could cut down the number of frames you're drawing by like double, quadruple, hire less animators, and then just run a model on top afterwards to smooth out the animation. It's really, poggers. It like produces a bit of a crisis among, what's the value of the technical merit in art. So there's also stuff like that. I've also seen them apply it to like really old footage that's in very low frame rate, obviously, because it's very primitive technology, and like retouch it and improve the quality and improve the frames per second. It's really quite impressive. That's like a very particular situation to solve. It's not. When you're thinking of self-driving cars, you don't think of like, oh, but what if I like want to cut down on the number of animators I have? So the problems there are really infinite, and there's always interesting developments to be solved. Next, I want to mention a bit about generative art. So in the middle here, we have 4 portraits. How many of them do you think were made by people? Zero, yeah. None of them were made by people. These are all portraits from Artbreeder. Artbreeder is a free website, and basically you can like select existing portraits on their platform and select the amount of one portrait you want blended in, and you can create a new portrait that has been generated from previous portraits. On the right here is a paper that I have linked at the end, where they have made a model such that you can give it an image and it'll basically paint over the image in a style of an artist that it has been trained on. So what's the website for that? I'll mention it at the end. So on the right-hand side, you can see they've taken that nice picture of like a quaint European town, and they've put some paintings over top of it. I think of this, these kind of examples as generative art. Whether or not they're still like in the computer vision realm, that's maybe up for the debate. Maybe this is in a bit of a blurry zone. I personally still think of it mentally as an area of computer vision, because it does work upon and has to consider visual cues that exist in the real world, or acknowledge some structures that occur in the real world. A person's face has eyes, nose, lips. Acknowledging those, or also like looking at that, the one on the right, looking at the real world and acknowledging, okay, these are the structures I have to work with. How do I apply that certain style on top? So those are some areas of generative art. All very cool. All very new and advancing. So yeah, that's a bit about the deep learning solutions. Any questions before moving on to the Detectron II coding example? I've seen a lot of activity in the chat, but I've not been keeping up with it. Thank you, Tina, for linking the website. The bottom right looks like my PC trying to run Cyberpunk. Ha! With my background in CV. My background in computer vision is I have taken one computer vision course at the University of Waterloo, CS 484. Yuri is a really great prof. I can talk more about the course at the end as well. I honestly don't have a lot of experience in ML. It's something that I'm still learning in, and yeah, that's my formal experience in CV. Otherwise, I generally like to read papers when I see interesting ones that come across my radar, and I love watching 2-minute papers. I know that's more of like a computer graphics type of channel, but yeah, there's just like a passive interest as well. How do you take over the government with computer vision? Surveillance is an incredibly big field in computer vision that I don't know how I feel about. Some of the biggest computer vision tech startups are Chinese surveillance startups that are very good at facial detection. How else do you want to go with the government with computer vision? Deepfakes are a bit of a concern I have. That's also a computer vision problem. You have to map a face onto a face. What year am I? I just completed my 3B term, and I'm in co-op right now, and I'm going to start 4A in the summer. Recommendation for 3-year computer science courses at Waterloo. Computer vision, which is CS 484. If you love this stuff, I strongly suggest you take it. I previously didn't know that computer vision had so much machine learning in it, which is kind of a dumb assumption. But there's also a machine learning course at University of Waterloo. So if you take those two together, I think that's a very nice combination. I wish I took machine learning last semester because I think it would have complemented computer vision very well. But you'll get by with just computer vision too. How is CS 484? I heard it's mostly legacy techniques like edge detection. Yeah, a vast majority of the course is spent on traditional solutions, or as you mentioned, legacy techniques. And that might feel like that's kind of useless, but I think it's in. I think I was thinking the same thing throughout the course, but I have grown to really appreciate it. I think it really helps to understand those legacy techniques in order to continue studying the deep learning aspect of it. Like I mentioned with the single view depth estimation, the clever loss functions that I kind of glossed over, you really had to understand how depth perception worked in order to write those loss functions. So it's still incredibly important. I think it's part of that, like, being disciplined and patient with your learning. But if you just want to run into it and just like tinker around with models and stuff, and you're not interested in a long-term career in the area, I think like just keeping up with it on your own time is good enough. Oh boy, sorry, I'm really backlogged on these questions. How's ECE? Unfortunately, I'm not in ECE. If anyone else is in ECE in this course, in this chat, please do let Andre know. Any resources to learn more CV? I'll have information in the information's in the hacker pack as well as at the end of this. Yeah, I'm seeing a lot of questions about resources. I'll be discussing that at the end. So stay tuned. It's also in the hacker pack as well. What's my favorite library to use? What's my favorite food to eat? What's my favorite color? I guess people usually have an answer for favorite color. I can't say I have a favorite library to use. I'm most in terms of CV and ML. I'm most comfortable with PyTorch, but that is mostly biased towards just what I've been learning so far, and the opinions of my TAs and professor. That's Pog, yeah. What's my favorite anime? Full Metal Alchemist, Brotherhood. Yeah, the original one's okay, but Brotherhood's definitely my favorite one. Good answer, yeah. Attack on Titan. I am not caught up on Attack on Titan. My friend like crash coursed me into the plot, and it's pretty crazy. But I definitely didn't keep up with Attack on Titan. I won't spoil it. Don't worry. All right. I think I'll have another section for questions at the very end. But I think it's a good time to start going into the Detectron example. All right. Let's jump into this. So what is Detectron II? Earlier I had mentioned, the scary black box with tuned weights. Detectron II you can think of as the black box where the weights have already been set. The model has already been trained. And so you can download it yourself and apply it to your projects and use a correctly trained model already. It is open source. You can find all the code about it on GitHub. It's made by Facebook AI. It's very well documented. I'm only really touching the surface of it, so do check it out if you're interested. And it's state of the art. It's pretty good. It's pretty good, and we'll see that in a second. And a bit more prereq before our coding example. What is Jupyter Notebook? What is Collab? Not super important that you know this stuff, but I'll go over it pretty quickly. Jupyter Notebook is a machine learning and data science Python tool. I won't get into detail of it, but it's really easy to like prototype some Python stuff really quickly, and there's also a very handy library in it that helps you visualize very quickly as well. And Collab is like basically the Google Drive version of it. Like you can't quite edit it on it as nicely as like a Google Doc, but it's all stored on your Google account. If you have a Gmail, you have a Collab. And every time you make a new notebook on Collab, it provides you a nice and clean environment. So if your personal computer is, I don't know, like you're busy training other models on it or whatever, or you have like a gazillion weird dependencies, don't worry about that. Collab is giving you a clean environment. And if you are interested in making your own models, which we're not doing today, but if you are interested in that, there is free GPU to train your models. They give a pretty generous amount. Honestly, it's like, it's free. I'm not gonna complain too much. There is a premium plan, but anyways, if you just want to like play around and train, a few models haphazardly, their GPU is like 12 hours of free time, I think. So that's a useful resource, especially if you're, a student in this area. All right, let's open up Collab or Jupyter Notebook if you're following along with that. Let me just pause my screen for a second as I get that open. Oh, now you get to look at my face. Okay, let me get out of the presentation. One second. All right. You want to donate a 3 cents? Me too, buddy, me too. All right. Okay, I have a clean Collab open. You can follow along if you're interested, but honestly, if you just want to sit back and chill out, that's perfectly fine too. Let's get right into Detectron. So, just full disclosure, I'm gonna have to keep the hop-in tab closed, so I'm just gonna like flip in between every once in a while, but I'm not gonna be able to see your questions as quickly. Okay. So first, let's install Detectron II. So for those unfamiliar with Jupyter Notebook, oops, that's awkward. Those unfamiliar with Jupyter Notebook, all the code cells are in Python, but if you just throw an exclamation point in front of it, you're like basically doing like a normal command line type thing. So Detectron is actually a pip package, which is really nice. You're not always going to get that with oh no, you're not always going to get that with these models, but very simple to get going. So this, wow, I cannot spell today. This is just going to help us visualize our pictures and our results. And I'll just import everything we need from Detectron. All right. So I have two images prepared for today, and I'll just help us talk through it a bit. First, I'll just show you what the images are, because it might get a little busy with the bounding boxes. All right. Ah. Oh, I didn't run this one. My bad. Run your cells in order. Oh. All right. Some delicious fruit. Eat your fruit, kids, or else you're gonna get scurvy. Now let's get that model from Detecto. So we'll take a core model, and I'll just take a second to load it. Ooh, ResNet 50. And well, that's going all get started on actually visualizing it. So you're gonna get labels, boxes, scores. Hold up, predict up image. Visualize dot show image. And if this is super confusing, don't worry, I'm going to break it down in a second. I just want to show you the nifty machine learning technology. Wow, dining table, apple, orange, revolutionary. I'm blown off my feet. Let's unpack this. Like, what's going on here? Print, labels, like what in the world are the labels? What are the boxes? What are the scores? Give it to me. Boom. Okay, let's dissect this. So we have the labels are pretty self-explanatory. You know what's up here. We got oranges, a dining table, and an apple. Let's go into what boxes are. The boxes are what's being drawn here. It's going to give you your x, y of the top leftmost point. And then it's going to give you the width of the box and then the height of the box. So also the position of the array or tensor in this case will be correlated along all these like labels, boxes, scores. So for the orange, we've got the x at 221, which looks about right. Y at 64, yep, and then the actual whatever. And then dining table 519, yeah, that's about right. And then scores. So scores is like basically giving the model is like giving you what degree of confidence it actually thinks the thing it's drawn as an orange is an orange. So it's really confident about the orange. It's giving us 99%, serving that up. It's giving us 94 on the apple. It's giving us a lot lower on the dining table, which is pretty understandable. I mean, if you think of viewing this as a person, for all you can know, it could just be sitting on like, flooring that is very well kept and shiny. So this is like just a way to intuitively kind of understand this. If you're a machine learning pro in the chat, sorry if this is like, very, very basic information to you, but I think this is, a good way to kind of understand it, get to know this information for those of us who are more new to computer vision. So let me move back to Hopin and just take a look at the chat. Implementing your own ML library is the way. I'll see you when you get your PhD in computer vision and you make your big pip package. Is the code going to be shared? Yep. Where's the YouTube link? I think it'll be generated afterwards. Oh, never mind. There's the YouTube link. PyTorch is the way, TensorFlow. Okay, I think I'll move on. No real questions here. Yeah. Oh yeah, and if you're curious, PyTorch is what I believe the Facebook AI team has used for Detecto. That's just if you're curious, though. All right. So that was pretty simple. Let's grab the next image and do this example again. So I'm just gonna. Now we're doing a cat. Look at that cat. All right, I've got you a cat meme. It's another glossy-eyed Photoshop cat. Me, hole in my heart, sad cat memes. That's filling the hole in my heart. Do you get it? It's funny. I'm hilarious. Anyways, next let's actually like run the model on top of it. Oops. I want to do labels. Oops. Boxes. Scores. Model.predict top image. All right, and then we're gonna visualize that. I'll just grab this. Should have done that earlier. Okay. So let's see what mess we're gonna have. Also, I realize we're running a little slow on time, so low on time, so I'm gonna speed this up. But wow, this is a disaster. Let's unpack that. Grab this. Bam, what's going on here? Why do we have labels like skateboard and frisbee? Where'd the hair dryer come from? Couch, knife, dog. This is not a dog. Wine glass, okay, maybe a book. So this information is definitely a bit messier to go through, but I think it's worth understanding it a bit. As I mentioned with the scores earlier, you can see that like it's not giving me a great number for skateboard, not giving me a great number for person. It's giving a pretty good number for 93% for cat. Like it can tell there's a cat involved. And it's giving us a pretty low number for dog, actually. So it's fairly certain about the cat. But like, why is there so much garbage here? And I think it's important to understand that this is a pretty weird picture. In most normal circumstances, you're not going to have a cat that has text over it that is holding a beer cup and getting poured a beer in this kind of like weird background as well. Like as a person, I don't even really understand what's happening in the back here. And so it's, I think it's important to recognize that the models are going to be really impacted by what data you're training it on. And my guess is the Detectron II training image set did not include cat memes that are photoshopped and really poor quality. Like this thing's only like barely 200 by 200 pixels. And it might be easy to be like, oh, silly Facebook engineers, like, oh, they should have predicted my cat meme. But another thing to ask yourself is also like, man, what's the point of training a model to be like ridiculously robust to catch everything, right? Like there's time that is valuable, and there's plenty of practical applications where Detectron is doing a great job. I mean, even here, like giving cat 93% is really good, and you could always just like kick out all of the results that came back with lower than 50% if you wanted to, right? So I just wanted to show this as an example of how to think about what you're actually feeding the model, and also to if you end up in this kind of situation, just I'm gonna kick out these. I'm gonna kick out the results with really low scores because it's just not worth my time and they're just too inaccurate. So hopefully this was helpful in understanding kind of like the basics of how to work with one of these models. Oh, okay, something I did not mention that I really should mention. PyTorch and these like machine learning libraries, lots of people know them very well, some people don't, and I think it's fine if you don't know them very well. They often use tensors to represent arrays. Tensors are really similar to NumPy arrays, if you're familiar with NumPy. I personally like to call it NumP, but anyways, if you're familiar with NumPy, tensors are really similar to those. If you're not, it's just like a really efficient way to store numbers in arrays for like really effective and quick math. I won't get too much into it, but if you're new to this kind of stuff, you can index it just like an array, and you can convert it to a normal array. You'll just have to look up the documentation because I don't know it off the top of my head, and we're also running out of time. But let me switch back to the slides because I still have a few slides. Humpty Dumpty Dumpty. Yeah. All right. So we're back from the example. How do I actually put this all together? So, you're new to computer vision. Maybe you're new to hackathons, and you're like, oh man, this Detectron II thing's pretty cool. In terms of putting it together, there's actually an intro to APIs workshop right now, but Hackathon will be posting the videos of it. And kind of from a high level view, describing how you can, put this into a project. You can make a Python API and directly respond to requests with Detectron II. You can get a pretty, simple hello world program going pretty quickly using Detectron II and making a Python API and kind of take it from there. Now, if you're not interested in object detection for a hackathon project in the same way that we've seen object detection, today, Detectron II has a lot more features in it. I've barely scratched the surface. On their GitHub repository in their project section, they have a ton of examples. Some of the most interesting ones I've seen are pose estimation and panoptic segmentation. So if you're interested in those, check them out. Pose estimation is when they draw a line through the people's bodies, always good for one of those, improve your dance or improve your workout form type of hackathon projects if that's what you're interested in. Some other, models if you're interested in computer vision outside of object detection for your hackathon project, monocular depth estimation, single view depth estimation is the thing I did for my final project that I mentioned earlier. You can look into that. There's 3D semantic segmentation if you wanna do things in 3D, or you have a LiDAR camera or something. There's other libraries for pose estimation as well. There's so much information on Papers with Code. Papers with Code has a lot of papers and code that goes with them. The papers will solve something specific like monocular depth estimation, and the code that goes with them often contains the trained model. Each library, each repository has its own kind of setup, so you'll have to do a little bit of legwork to read through the repository and figure out exactly what you have to do to set it up. But people are great part about open source and that kind of community is people will post their trained models, and you can download them and get working with them right away. So lots of options there if you're not interested in object detection for this hackathon project, or if you're not interested in Detectron II for your hackathon project. Making your own model, as I mentioned, if you're trying to do this for the hackathon, you might spend the entire hackathon training your model, and that's not very fun, and it's definitely not going to be fun if you get to the end of it and you realized there was something wrong with your loss function and it doesn't look great. But it is an incredibly good exercise to better your understanding of machine learning and better your understanding of computer vision. So establishing a productive machine learning workflow, check that out. That's another workshop in this Gear Up series. And implementing papers directly is a really good exercise. The molecular depth estimation project, we literally just found the paper from the team and implemented it. They give you really great step-by-steps. Some of the math might go whoa, right over your head, but if you're patient, you can work it out. You can make your own models. You can train them. They'll even tell you what data sets they use and how to download them. It's a really great exercise if you're interested in strengthening that part of your understanding of machine learning and computer vision. So this is actually just copy-pasted from the Hacker Pack, but we're actually going to start from the bottom. I mentioned implementing your own papers. If you're interested in that, there's a really great Reddit thread Link is on the Hacker Pack and in this presentation with tons of papers that I'm also slowly getting through. They're good to read and they're also good to try implementing. And some people in that thread have given their own opinions. There's also some different users on GitHub who've posted lists of interesting papers. I like Footsong's deep learning papers reading roadmap if you want something a little more structured to get through. All right, other resources, we'll start at the top again. There is a more advanced Collab tutorial from the authors of Detectron II, and they include how to use Detectron II as a checkpoint if you want to build a model off of that. So there's information there. Other ready-to-use models, as I mentioned, you can browse papers. PyTorch will be important to understand a bit about PyTorch. We're going into that. And about computer vision courses, if you're a UWaterloo student or you're looking to go to UWaterloo, CS484 is the course that you wanna be part of. Yuri, the professor, is a really big name in computer vision, very knowledgeable in the field. The TAs are great. I highly recommend the course. It's really interesting. There are a bit of prereqs. If you're a CS student, the only thing you have to go out of your way to take to get into computer vision is CS 370. So just take that in 3B or 3A. Actually, I think you have to take in 3B. And a strong linear algebra background will be valuable especially in like the first half, a bit of the second half of the course where they're really focusing on those traditional solutions. A lot of that's math-based. I struggled a bit because I have a bit of a weaker linear algebra background, but I made it out of the course alive and I still like computer vision. So if you don't have a very strong linear algebra background, I don't think it's the end of the world. There's also a Udacity course and Coursera course. I haven't personally taken the courses, but I looked through their syllabi, and they're quite similar to the CS484 syllabi in many ways. And they do spend a decent amount of time patiently getting you to understand the traditional solutions. So if you're interested in that more structured learning, I suggest you check it out. All right, so here's the question segment again. I know the chat has been popping off, so let me take a look again. Okay, lots of cat-related memes. The Tektron was made really complex, and here we are making analyze a cat meme. Yeah, innovation starts here. NumPy. Do I have Kaggle? I do not have Kaggle. The other CV course at Waterloo is, other engineering programs also have computer vision. I'm unfortunately not as familiar with them, but definitely check those out. Who's the professor for this course? Yuri Boykov is the professor for CS484. He's done some great work in segmentation, in particular in the k-means stuff. That was the picture with the rows, and that was blobbed into its average color. He's done a lot of work in that area. Tips on how to get into Waterloo CS. Maybe we can talk after. Will the slides be posted somewhere? Yes, I will be posting the slides. In the Hacker Pack, there is a link to a repo where the Collab notebook is downloaded and posted. The cat image and the fruit image are posted. The slides are out of date, but I will be uploading them again after this. So the slides will be available there. Oh no, did I ignore someone's question? Sam, what was your question? Sorry about that. There's a bit of a dense chat. Would it be? I'm unsure. Consult a lawyer. I will not give out legal advice. All right, it seems like the chat is slowing down a bit. And I am 11 minutes overtime, so apologies for running overtime, but thank you so much for coming out today. I will be on the Discord on the machine learning channel. If you have any more questions, you can also tweet me or email me. I'm very responsive on both forms. I'm happy to answer any questions. I'm happy to talk about like really anything. This computer vision, if you just want to chat or anything like that, hit me up. No problem. Thanks for coming out to the workshop. And good luck at the hackathon, everyone. Thank you, thank you. I don't know if I'm supposed to like leave the workshop yet, so I guess I'll just hang around until the chat empties out. There's an intro to open source and an intro to Docker workshop at 9 p.m. if you're interested in those. Have you worked with CV and self-driving vehicles like with Ross? No, I'm unfortunately not very familiar in the self-driving vehicle area. It would be very cool to have an opportunity to work on that stuff though. If you're a Waterloo student, even if you're, I guess if you're like any university student, a lot of schools have like those design teams where they're building self-driving cars. So that would probably be a really good place to learn that if you're interested in. I have not taken the initiative to join those groups, but they are definitely doing some pretty cool stuff. Where did you get the lit jacket? I actually was an organizer for Hack the North for 2018 and 19. So join the Hack the North organizing team and you'll get a jacket. Yeah. But just kidding. Please be more intrinsically motivated to organize the hackathon. But yeah, join the organizing team. Yeah, Annie's on the organizing team. Lots of people are on the organizing team. It's cool. It's lit, yeah. This was the bomber. Oh my, in 2018, I really wanted the team jacket to be a bomber, but like only 2 other people agreed with the bomber. But then 2019, everyone wanted the bomber. So I'm really happy that I got the bomber in the end. Yeah, yeah. Yeah. Anyone watching anime lately? I need something to fill the void after finishing Haikyuu. I'm happy to wait around for questions. Finish Death Note. Oh, cool. Yeah, I'll just stick around until the like chat empties out. I'm happy to. Oh, just finished Ava. Better watch the end of Evangelion too, and then watch all the reboots. I hear 3.0 plus 1.0 is gonna come out with just all the Ava weird plot you love and 10 times more fan service. Yeah, follow-up questions can go into machine learning. I have it open right now on my other laptop, so yeah. Mr. Robot, I have not heard of that one. Oh, that's cool. I have to look it up. Mr. Robot. Interesting. There's another like kind of techie Netflix movie. I think it's The Social Dilemma. It's the one about advertisements. I haven't watched it yet, but the guy who was one of the writers, I I was about to say I respect him a lot, but I can't even remember his name, so I guess that's a bit of a lie. But anyways, I hear that one's really good, but I haven't gone around watching it. Plug, bro, plug. Yeah, if you're interested in finding teammates for computer vision projects, I guess this is a good place to find teammates as well. As well as the like machine learning channel if you wanna jump there. Yo, Ryan's just doing self promo. Man's gotta hustle. I respect that. All right, I'm gonna jump over to Discord and upload these slides. But again, if you have any questions, leave them in the Discord, tweet me, email me. But yeah, it was lovely to present the workshop today, and I hope you all have a good time. And if you're participating in the hackathon, good luck on the hackathon. I will be ending the stream now.
Hummus.